Once again, good afternoon to all. Yesterday, what we have seen is how we are going to select the belt, and what we have seen is the types of belts as well as their applications. And type-wise, we have seen advantages and disadvantages also. So, last slide which we have seen to the yesterday's lecture is this slide, and in which we are going to further move, and we are going to see, or we are going to concentrate basically on the selection procedure of the belt. Let me know if you do have any question related to the previous slides. If not, we are going to move further. Now, when we are going to see design of flat belt drive, okay, not only flat belt drive, but for the V belt drive also, we are going to use the same or somewhat difficult procedure than the flat belt, because in that case, little bit it is difficult as compared to the flat belt. So next slide, which we are going to see, when we are thinking about the belt and belt drive to be used for the machinery, at that time we are going to have two options. Either we can design that belt drive. Okay, designing means everything we have to design, that is right from pulley, then belt, its material, its length, everything. That is one option which we can choose. Here it is written at the second number. And first option is that is designing flat belt drive or V belt drive using manufacturer's data. And in previous lecture, I was talking about it, that is manufacturer's catalog or standard design data book. If you see these two methods which you can use for the selection or for designing of that belt drive, the first one is what we can say, it is very easy, and second one is time consuming, and in which we can concentrate on that first one, where we can select the belts from manufacturer's catalog. Okay, and this first method or first option is widely used in machine design, because you know what, if you are going to waste your important time in such part which you are going to use as a some additional or supportive type of that primary machinery which you want to design, then it will become time consuming procedure. Okay, that's why already I have told you that some standardization is used in design, like the common material which we are going to use everywhere in every machinery, like screws, then bolt, nut, couplings, they are readily available in market, and we can concentrate on the functioning of that machine and new modification, new invention of that machinery. Or we can redefine that problem and we can have some new way of solution for the traditional problem. Okay, so here we are going to concentrate more on the first part, and this latter part that is not actually included in syllabus. So if you are going to see the selection of belt, first of all, we'll see selection of flat belt, and later on we'll see selection of V belt. Now, first thing that is, we'll see selection of flat belt. So when we are going to select the flat belt, for sake of simplicity, we'll call it as a design of belt also, belt drive basically, not only belt, belt drive. And in which we are going to see the procedure by means of which we can select that flat belt from manufacturer's data or manufacturer's catalog as per our requirement, as per the machinery requirement. So the steps which are involved in the selection of flat belt are these 10 steps. So first of all, we have to determine the pulley diameters. Then second step is that speed of driven and driving pulleys, N1 and N2, which we are going to call. Driving pulley is rotating with N1 speed and driven pulley is rotating with N2 speed. So we have to calculate the speed, or we should know speed of driving and driven pulley. Then third step is that design power in kilowatt. That is, we have to calculate power which we have to transmit with the help of this drive. flat belt drive. So it is called as design power. So rated power, that is nothing but the regular power which you want to transmit from one shaft to another shaft with the help of flat belt drive. But we have to add, or we have to use some factors, and by means of which we can calculate the design power. Okay. So definitely this design power is higher than the rated power. That is nothing but the actual power which that drive is going to transmit. Then fourth step is that we have to calculate belt velocity or velocity of that belt in meter per second. That is, we have to calculate linear velocity of the belt. Okay. Fifth step is that we have to do selection of belt, that is high speed or forward belt. Okay, this high speed and forward belt we are going to see in details when we are going to see all the steps in details. Okay, just here I have mentioned the steps through which we have to go for selection of flat belt. Then sixth number is that we have to find out how many number of plies to be used for that belt. That is, plies are nothing but the what we can layer of that belt, because belt is manufactured in layers. Okay, so how many layered belt we have to use, that we are going to decide at this stage. That is stage number 6. Then at 7 stage we have to calculate load rating according to the speed which we have calculated, linear velocity which we have calculated for the belt. Okay, so we have to select this load rating for the given or calculated linear velocity of the belt. 8th, we have to see belt width. That is, we have to calculate the belt width, and we have to select it from the standard catalog which is available. 9th number is that once you decide this belt width, we have to decide width of pulley. And 10th number, we have to calculate length of that belt. That is total length of that belt. Okay, these are the 10 steps which we have to follow, and that are followed again sequentially. It doesn't mean that after calculation of pulley diameter, we cannot calculate velocity, that is velocity of the belt. But unless and until you are not going to find out this driving and driven pulley speed, we cannot calculate velocity of that belt. So we have to follow this all step or all these 10 procedures step by step. Okay, one, then second, then third, then fourth, then fifth. Likewise, we have to follow it step by step. Okay, so once we go through all these steps, we'll able to design the required belt, flat belt, or we'll be able to select rather than designing. Okay, I can use word parallel word as a selection. Okay, now here for this particular chapter only, I am going to say that this design word is parallel to the selection, but in rest of the other cases it is not. It is actually we have to design, we have to calculate the stress, and we have to calculate the dimensions. So this all procedure we have to follow. Now we'll see step by step this procedure and what exactly we have to do in each step. So in case of first step, we have to find out the diameters of that pulleys. Okay, for sake of simplicity, here D, capital D and small d is used. Small d is used for the driver and capital D is used for the driven pulley. Now here we are going to consider, note is placed here. You can read that note. It is placed as, here we are assuming that the driven pulley is larger than in diameter than the driving pulley. That is, here we are going to consider that driven pulley is smaller one, for which we are going to use abbreviation as a small d, and driving pulley is smaller and driven pulley is bigger in diameter as compared to the driver. Okay, so in this step, basically the dimensions are given in the problem statement, and if that diameters are not given in the problem statement, we have to calculate that dimensions with the help of this formulae, and this formulae is n1 divided by n2, where n1 is the speed of driver, n2 is the speed of driven pulley. and is equal to capital D divided by small d, where capital D is the diameter of larger pulley and small d is the diameter of smaller pulley. Okay, so this very simple relationship between speed of that pulley and diameter of that pulley is written. Any question related to this? If all these things are given in the problem statement, then not necessary to do this calculation, because speed of driven pulley and driving pulley, if it is given, and diameter of that respective pulleys are given, then we are not going to calculate it. We are going to use as it is for the further procedure. Any question? If you have any question, you are free to ask. Otherwise, we'll go to further step. Let me know if you have any question. If not, no, okay. So we'll move to the further slide and further step. Now, after finding the pulley diameters, as it is, we are not going to use for the selection of the belt. Okay. What we have to do is that once we are going to find out the pulley diameter accurately, then we are going to select that pulleys or diameter of that pulleys from the standard data which is available from the manufacturer's catalog. Okay, so we have to find out, suppose we got that diameter of driving pulley or diameter of smaller pulley as 56.83. Hello, can you listen me? Shubham, can you listen me? Yes, okay, no problem. Thank you. So if we are going to get the driver pulley diameter as a 56.83, then we are not going to select pulley diameter, standard pulley diameter as a 56. We are going to select the next one. So here, if we are going to get value as a 56.83 millimeter, that is the diameter of driving pulley, then this 56 standard diameter pulley we are not going to select. We are going to select next one, which is available. Now, once we are going to select the next one, that is 63 millimeter diameter pulley, then definitely what will happen? Again, we have to go to the first stage. And here, because if diameter is going to change, definitely speed is going to change. And we are going to select, or we are going to find out the diameter of that driven pulley. Once you decide diameter of driving pulley from the standard pulleys which are available, dimensions which are available, from that we have to calculate based on the velocity ratio or input that driving pulley speed and driven pulley speed. Based on this relationship, we are going to calculate again diameter of the driven pulley. Hope that you are getting what I am saying. I will repeat it once again. By means of calculation or given data, we can use that data for finding out the standard diameter pulley. Okay, so these diameters are in millimeter, standard pulley diameters. Okay, if we are going to get value, okay, I will take another example. If we are going to get value of driven pulley, or sorry, driving pulley will take example, then we can calculate driven pulley. But if we are going to get dimension of that driving pulley as a 53 millimeter, now in this series 53 is not available. What is available is 50 and 56, right? So all calculations we have done for the speed ratio and velocity ratio based on 53. But while we are going to select the driving pulley diameter, we are not selecting as a 50, we are selecting it as a 56. Next one we are going to take, okay? Because previous one, if you are going to select which is less than the actual value and which is not recommended. In case of designing also, we have seen if we are getting dimension of any component in fractions or in not in standard, then we are going to select the next value, right? So likewise, we are going to select this 56 diameter of driving pulley, and using this equation, we are going to calculate diameter of driven pulley, okay, based on velocity ratio. That is what we are going to see here. Okay. If note is placed here, if you are using PSG design data book, refer page number 7.54, and that edition is of 2012, reprinted it is. Okay, for finding the standard pulley diameters, for finding these values. Okay, if you are using manufacturer's catalog, then it is given and heading is given also on that catalog, that standard dimensions of the pulleys or standard diameters of that pulleys. And if you are using PSG design data book, then you'll find it on page number 7.54, and edition which we have to use is 2012 reprinted. Okay, this is available in market now. If you are using previous editions, then this page number is different. Getting? So after selecting the standard dimensions of the diameters of that pulley, we have to move further and we have to follow the step number 2. In step number 2, we have to find the speeds of driving and driven pulleys. Now you can ask question that, sir, already we have used this equation to find out the speed ratio and velocity ratio. Then here again we are going to find the speed of driving and driven pulleys. Now in some cases, some problems, this speed of driving and driven pulleys will be given. But if it is not given, okay, then we have to use the formula, previous formula, that is nothing but the same formula. From the diameters, we have to calculate the speeds of driving and driven pulley. In problem already either diameters are given or speeds will be given, or in problem statement either speed of any one pulley will be given. Okay, later on we can decide the speed of other pulley based on the velocity ratio which is required. Because if you are going to use the standard prime movers to operate that machinery like motors, electrical motors, then you will have standard speeds of that motor like 1440 rpm for 7 HP to 10 HP motors, right? Likewise, we'll have a standard speed which is available for that particular prime mover. But if you are taking example of windmill, then in case of windmill, input speed is not constant. It is depend upon the velocity of wind. But in case of windmills, we should get the output as a constant speed. And that's why this design is oriented in that way. In that case, if you are using belt drives, then we have to consider all these things for which we are going to design, or for which we are application we are going to follow this procedure of selecting of belt. Okay, but such applications are less where the speed may get fluctuate. Okay, like in case of windmill, and in case of windmill, we are not going to recommend belt drives, or their gearboxes are used. But keep in mind that we have to again consider that fluctuation in the speed. In some applications or in some problems, it is given. Suppose in some problem, they are going to mention percentage slip of driving pulley and driven pulley also. If that's percentage of slip is given, then the previous formula which we have used, this formula is not applicable. For that purpose, we have to use some different formula which is written here, and that is N1 divided by N2 is equal to capital D divided by small d into bracket 1 minus S1 plus S2 divided by 100. Now this S1 and S2 are nothing but the percentage slip between the driving pulley and the belt, and S2 is the percentage of slip between belt and driven pulley. Got it? Any question? If the percentage of slip is considered as 0, we can use the previous formula. If the percentage of that slip is given in the problem statement, or it is said that we have to consider it, okay, then we have to use this formula for calculating speed of driving and driven pulleys from the diameters. First step is that we have to decide diameters. Second step is that based on that diameters which you have selected from the standard values or standard values which are available, from that you have to decide the speed of driving pulley and driven pulley. Got it? Again, in this case, there is one more criteria which we can decide, that if you are considering the thickness of belt, because all these calculations which we have done, this formulae which we have done is based on the neglecting that thickness of belt. Only we are going to consider diameter of that pulleys. But if you want to consider that thickness of belt also, if the belt is sufficient thick, and if you want to consider its thickness, then just what we have to do, that we have to add the thickness of belt in the diameter of that pulleys, and formula will be rewritten as N1 divided by N2 is equal to capital D plus T divided by small d plus T into bracket 1 minus S1 plus S2 divided by 100. And that will be the velocity ratio. But here, if you are going to consider percentage slip as a 0, then this part of the formulae will get value equal to 1. Okay, it will not affect on the speed ratio. But if the percentage slip is given, then we have to use this formulae. Okay, and additionally with the thickness of the belt. Any question? And more precisely, if you are considering the thickness, then here in this same formulae, instead of using T, you can use T by 2. Okay, because at the mid of this belt, we can consider as a neutral axis where the power is transmitted, by means of which the power is transmitted. But we are not going in such details. We can only consider the thickness of this belt. Any question? Let me know if you do any question. Are you getting it? Yes. Okay. Yes. Thank you. So we can move further, and we can go to the next step. That is step number 3. In this step, we have to find the design power in kilowatt. Okay, that should be in kilowatt. If we are going to consider that power in watt, then the tables which are available in catalog, they all are given in kilowatt rating. So for that purpose, what we have to do is that we have to calculate that design power in kilowatt. Now this design power in kilowatt can be find out by means of this formula. What is this formula? Is that design power is equal to rated power multiplied by load correction factor divided by R of contact factor multiplied by smaller pulley diameter factor. Now here you can see all these things which are new to us, that is load correction factor, arc of contact factor, and smaller pulley diameter factor. If these 3 factors are known, then we can calculate this design power from the rated power or regular power which you want to transmit through the flat belt. Now, one by one, we'll see what is this load correction factor, what is this arc of contact factor, and what is this smaller pulley diameter factor. Okay. So this third step is quite bigger, and we should have knowledge of this load correction factor, arc of contact factor, and smaller pulley diameter factor. Okay. Then this rated power is converted into design power, and based on this design power, we can select the belt. Okay. Any question? Have you got this stage? If yes, we'll go to the further step. Yes, okay. So in further stage, one by one we'll go. First of all, we'll see load correction factor. Now this load correction factor, okay, that is first what quantity which we are going to find out, is based on the application of that particular belt drive. Okay. Now here you can see one table. In first column, it is written as a type of load, which type of load you are handling with the belt drive, flat belt drive. Then where you are going to apply that flat belt drive. Then based on these two, here in third column, that factor value is given. Okay. So all applications for which flat belts are used are included in this table. So first type is that normal load, okay, normal load rating, and when minimum load is known, okay, that is nothing but the minimum and maximum load is known to us, then we are going to consider it as a normal load condition. While solving problems, we'll find or we'll come to know what is the range of that normal load, okay, and based on that we are going to decide this multiplying factor to the load factor as a 1. But this is very rarely used factor, okay. Normal load factor is very rarely used in selection of this flat belt. Our next stage is this steady load, where the steady load can be considered in light duty fans. If you are using belt drive for the light duty fans like the industrial fans, okay, now I'm not talking about the ceiling fan or table fan, okay. In that case, directly motor is connected to the fan. But in case of industrial application where fans are used for cooling purpose, okay, in that application, this steady load can be considered in light duty fans, okay. Then centrifugal pumps, then in printing machinery, in textile machinery, okay, then screens, then agitators. All these are the equipments which are used in food in the process industry, okay. Then evaporators and light machinery, okay, like lathe machine which you are using in your workshop. In that case also, we can select flat belts, but nowadays the flat belts are replaced by means of V-belt. But if you are going to see the old machineries which are used, that machineries are available in our workshop. You can see that old machineries also, okay. If you enter in the workshop, then to the right side, you can see the old machineries which are used, lathe machines. Big lathe machine is there. In that lathe machine, you can see these flat belts are used, okay. And to the left side of you, the lathe machines are bigger in number and smaller in size. They are using V-belts, but they are comparatively new machineries, okay. And that design change has been take place from flat belt to V-belt, okay. So that light duty machineries can be considered under the application of this steady load. In that case, you can use this load factor as a 1.2. Then next, intermediate loads, okay, that is normal. Then we are moving to the intermediate. Then here we are considering heavy machine tools like turrets, okay. Then heavy duty fans, like fans which are used for the large area cooling or for the crystallizing of you can say any chemical, okay. In that case, cooling rate is increased by means of fan, and if that heavy duty fans are used for that, then boilers, okay, then air compressors, big air compressors and blowers, then reciprocating pumps, then elevators which you can find in malls and other applications, then mill machineries, big mill machineries, then line shafts. Line shafts means the shafts where one shaft is used to run various machineries or different machineries. Then in case of paper mill and sawmill machineries. Okay. Now sawmill machineries which we are going to consider are considered as the bigger machineries, not smaller machineries which we can find nearby us. In that case, we can use this factor, load factor as a 1.3 load correction factor. Okay. Then next type of load is shock load. That is nothing but suddenly load is applied, like in hammers, okay. Then grinders, okay, crushing machineries, like stone crushing machineries, okay. Then desicators, then vacuum pumps, rolling mills, then tube mills. Tube mills means where you are going to manufacture endless tubes or pipes. then ball mills, okay, automated machineries, and stamp press, where you are stamping some what we can say, logo of any company or some impressions on a job. In such cases, we are going to consider that load which is applied is shock load, and in that case we are going to consider this load correction factor as a 1.5. Okay, you'll come to know that as this factor of load correction factor is going to increase, the rated power is multiply with higher number. This load correction factor here you can see this rated power is multiply with the higher number. Hence, possibly this design power will get increased. Right? Then definitely the power which you are going to consider to be transmitted by the belt drive, that will be higher than the regular power which will be transmitted with the belt drive. And that is just like what you can say factor of safety. Right? Do you get it? This table. Can we move further? Any question related to this table and third tab? Yes, you can write in chat box. Can we move further? No doubt. Okay. Okay, we'll move further. So next we have to find out arc of contact factor. Now, what is this arc of contact factor? Basically, we should understand what the arc of contact factor is, and for that you can see this diagram. In case of this diagram, you can see that the arc of contact between the belt and pulley is smaller in case of smaller diameter pulley. And if the bigger diameter pulley you are going to consider, then arc of contact, it is just geometry, right? So with this geometry, you can easily come to know that arc of contact for the bigger pulley is higher and arc of contact for the smaller pulley is smaller. But where I am going to compare it? I am going to compare it with standard 180-degree values. In case of same diameter pulleys, you can consider that the arc of contact is 180-degree. Okay, but if this such type of applications are rare to rare, where the diameter of pulleys are same, but we are going to use this belt drive, flat belt drive, where speed ratio is achieved. That is, speed of driving pulley is higher than the speed of driven pulley, where you can multiply the torque. You can get increased torque by reducing the speed. So in such applications, this arc of contact, then the standard arc of contact, that is nothing but 180-degree. In case of small pulley, it is smaller. And in case of bigger pulley, it is bigger than 180-degree. And because of that, we have to consider this arc of contact factor. Now this arc of contact or this arc of contact, basically we are going to calculate by means of this 180-degree, that is nothing but standard arc of contact, minus diameter of bigger pulley minus diameter of smaller pulley divided by C. Now C is center distance here, and this center distance is approximate center distance which we are going to take for the calculation. Okay, then exact center distance we are going to calculate at the stage number 3 or step number 3. Okay, multiplied by 60-degree. Now these values are taken in the degrees, and these diameters are taken into millimeter, as well as this center distance is also taken in millimeter. Okay, so after finding this arc of contact, we must change it to the nearest standard value. Okay, now this arc of contact value which we are going to get may not be the standard arc of contact which is available in that manufacturer's catalog. Okay, so what that catalog is and how that table is, that is mentioned in the next slide. Now here you can see the standard arc of contacts are mentioned here. That is 90-degree, 120-degree, then 130-degree, 140-degree, 150-degree. Likewise, it is up to 250 degrees. Okay, any pulley, that is smaller diameter pulley or bigger diameter pulley, will have arc of contact between this 90 degree to 150 degrees. And based on that, we are going to have arc of contact factor. Now, once you calculate this arc of contact, okay, 95 degrees, then we have to check that whether this 95 degree is available in the table. Now here you can see this 95 degree is not available in this table. So what we have to do, we cannot select 90 degree. We can go further to the next value, that is 120 degree, and you can select the arc of contact factor, which is Soham. Any question? Roll number 35, Soham.
No, sir.
Okay. So please don't unmute. Okay. Yourself. If you have any question, you are free to unmute. But in between, please don't unmute yourself. So this next arc of contact factor which you are going to get is 1.33. Okay. So this next arc of contact we can use. Now here you will come to know that as the arc of contact goes on increasing, this factor is going to get reduced. And if you see the formula by means of which you are going to calculate the design power, this arc of contact factor is divided with the rated power. It means that if the value of this arc of contact factor is going to get reduced, design power will get increased, right? It is vice versa with each other. So by using this standard table, and no doubt if the exam is conducted offline, then all these tables will be provided to you with the help of design data book, or it will be printed in your exam paper. Okay, that is question where when this exam will be conducted offline. Okay, so like this procedure, we have to find out the arc of contact factor. Any question related to this? Do you get the table? If you get it, then we can move to the further calculation of third factor. Let me know. You can write in comment box. Yes. Okay. Okay. Thank you. We can move further, and we'll see third factor, that is smaller pulley diameter factor. Now, this smaller pulley diameter factor is given in the standard table. Smaller pulley diameter factor can be found out using this table which has mentioned here. Now, this in this table, in first column, range of smaller pulley diameter is given, and correlated to that, the smaller pulley diameter factor is given. That is nothing but if suppose I am having smaller pulley diameter as a 15, okay, we have to check it whether it is available in standard dimensions of the pulley or not. If it is available, then we have to choose it. Okay, because in second stage we have seen that the pulley diameters are selected from the standard availability diameter or diameters of that pulley. Okay, so if for sake of simplicity we will consider that my pulley is of 15 millimeter diameter, 15, then directly we have to use the smaller pulley diameter factor as 0.5 because up to 100 millimeter diameter, we can use this factor. If the smaller pulley diameter is increased from 100 to 200 or in between 100 and 100 to 200 millimeter, then we have to use factor as a 0.6. Okay. Likewise, up to 750 millimeter diameter, from 400 to 750 millimeter diameter, we have to use the smaller pulley diameter factor as a 0.9, and all the dimensions of smaller pulley more than 750 millimeter, we have to use this factor as a 1. Got it? Once you calculate or find out, rather than calculation, we can say find out these three factors, you can calculate the design power from rated power. Okay. Any question? Can we move to the fourth step? Yes, let me know. Hurry up. Yes. Any question related to the up to third step? Can we go to the fourth step? Hello? Yes. Okay. Thank you. Now, fourth step is that finding the belt velocity. Now, in this case, belt velocity is nothing but the linear velocity of that belt by means of which it is moving. Now, maximum velocity of belt, which is denoted by letter V, capital letter V, and is measured in meter per second. Okay, can be find out using following formulae. This formula, that is V is equal to pi d n1 divided by 60, where it is considered that n1 as a higher RPM in case of both of that pulleys, that is driven and driving pulley. Okay, so speed of driver is considered as a higher speed. Okay, so this driving pulley speed is considered. That's why here you can use driven pulley also, but correlated to that we have to use bigger diameter, that is capital D diameter. Okay, or diameter of bigger pulley. No doubt, if you are not knowing a diameter of smaller pulley and speed of smaller pulley, you can use diameter of bigger pulley and speed of bigger pulley. But up to this stage, we selected diameters of both the pulleys, that is smaller one and bigger one, as well as we might have calculated or it is given the speed ratio, that is speed of driving pulley and driven pulley. Okay, so using this, V is equal to pi dn1 divided by 60, d where small d we have to use. This formula we can calculate velocity, linear velocity of belt in meter per second. Likewise, you have calculated linear velocity of any rotating link, okay, by means of this formula, that is V is equal to R omega. But in this case, omega is 2 pi n1 divided by 60 and R is d by 2. And if you are going to put these values of R and omega in this equation, first equation, that is V is equal to R omega, you will get this same equation. And provided that this radius should be in meter, okay, speed should be in RPM, then this velocity which you are going to get is in meter per second. Got it? And once you find out this velocity, linear velocity of belt, then we can move to the next step, that is step number 5. We have to select the type of belt. Okay, type of belt means it is not the case that V belt or flat belt or grooved belts. Okay, but the first company or company which has made standardization in the belt and which has given by means of which we can select the belts is Dunlop. You might be knowing Dunlop company. Okay, so in this case, this Dunlop has given two types of belt. One, okay, this is name which is given by the company, okay, not by any scientist or engineer. So, but it is used worldwide and it is considered as the standard name which we can provide to the belt. So first type is high speed 878G, okay, duck belting. So this is first category of the belt, which is used in light and medium duty applications with high belt velocity. If the velocity of belt is high and power rating is as compared to the other applications is small. So it is used in light and medium duties, okay, where the high speed is there or high velocity is there for the belt. And second category is Dunlop Fort 949G duck belting. Now this Fort 949G duck is what the name which is given by the Dunlop company. Okay. So this is used for the heavy duty applications and with the moderate speed, where the speed is less as compared to the previous case or first category. Okay. So again, how we are going to design or how we are going to consider this high speed or this port. Okay, for that again guiding statements are given. For design power less than 20 kilowatt and belt velocity greater than 16 meter per second, you can select, okay, these values you have to keep in mind. Power if it is less than 20 kilonewton and velocity is more than 16 meter per second, it will coming under the first category, high speed and low power. In that case we have to use this high speed 878G duck belting. And if the design power is greater than 20 kilowatt and speed is less than 16 meter per second, then we can select this port 949G duck belting. Any question related to this slide? Let me know if you have any question up to step number 5. Okay, if you don't have any question, we'll move to the step number 6. In case of this step, what we have to do is that we are going to determine the number of plies which we can use for the belts. And for that, this table is used. Okay. Now here in this table, that first column is for the number of plies, and from second onwards, first row is used for the diameters of the velocities of the belt. Okay, and from first rows onwards, that is second, third, fourth, and all other rows, they are for the diameter of the pulleys. Okay, minimum pulley diameter, that is smaller pulley diameter. Getting? So note is given here. In above table, the values given in italic are the values of minimum pulley diameter in millimeter. And this first row is for the belt velocity in meter per second. Now this belt velocity varying from 10 to 30 meter per second, that is from low to moderate velocity. And pulley diameters are from 90 millimeter to 710 millimeter. Okay, that is the diameter of smaller pulley. So based on this combination, suppose I got velocity of belt in between 15 to 20 meter per second, then I cannot use, suppose it is 17 meter per second, then I have to choose the next one, that is 20 meter per second. And if the pulley diameter is 180, then I have to use 4 ply belt. Are you getting me? This 20 and 180. Here we are going to get as a 4 plies. 4 ply belt we have to select. If suppose rated power or design power is in such a way that we get the velocity as 25 meter per second, and our smaller pulley has a diameter equal to 400, then this 25 column we have to get where the 400 is there. We have to select this 6 plies belt. Getting me? If suppose we are getting speed as a 25 and smaller pulley diameter as a 315, which ply we have to select? Are you getting my question? If speed is 25 meter per second and diameter of smaller pulley is 315, yes, 15. Whether that speed should be considered as a 15 meter per second? Do you want to say this, Shubham? Yes, okay. No, we are not going to consider that belt velocity as a 15 meter per second, but we are going to consider it as a 25 meter per second only. Okay. In that case, if suppose we are selecting this 315 millimeter diameter of smaller pulley, then also we are getting these 6 plies. Okay. And here, if you are considering that pulley diameter is 400, then also we are going to get this 6 plies only. So it is not necessary to go for the smaller one or velocity column where the smaller value is written. You are going to select that same value of number of plies which are used. Okay, such complications will not be there in actual problem. Okay, but this pulley range are decided in such a way that you can use the rated number of plies for the transmitting of that power. Any question? Let me know if you have any question. Otherwise, we'll move to the further step. Step number 7. In case of this step number 7, we are going to find load rating at calculated linear velocity of the belt. So in this case, for the high speed, we are going to use at least 0.0118 kilowatt, which can be transmitted per millimeter width of that belt per ply. See, you can read it once again. I will read it once again. If you are selecting high speed type of belt, and if you are having width equal to 100 millimeter, okay. So per millimeter power which can be transmitted, that can be considered as a 0.0118 kilowatt, and that is again per ply. If you are using 4 ply belt, it will multiply by 4, and if width of that belt is 100, then again you have to multiply by the 100 multiplied by 4 multiplied by this value. Getting? For the port, that value is 0.0147 kilowatt per millimeter width of that belt per ply. So for the high speed, this corrected factor or corrected kilowatt rating will become 0.0118 multiplied by V divided by 5.08, which is equal to the 0.0023 kilowatt per millimeter per ply. Okay, so that is corrected one, which is correlated with the velocity, that is linear velocity of the belt. And for the port, this value is 0.0289 kilowatt per millimeter per ply of that belt. Okay, so this you can write your roll numbers in your chat box, and after writing your roll number, okay, you can leave this meeting. .08 value. Okay, this question is asked by Shubham. Okay, Shubham, we will discuss about this in the next lecture. You please ask or remind me, or I will definitely give the answer. Yes, no problem. Yeah. So thank you for listening me.